My name is Ankur. I work at Fiddler Labs. I've been at Fiddler for the last 4 months. And before that, I was a research scientist at Google. I'm going to tell you about some research actually on explaining machine learning models. This is work that we started in 2016 while I was at Google, and now I've been continuing it at Fiddler. So most of what I'm going to tell you is sort of joint work with colleagues at Google and colleagues at Fiddler. All right. So we all are familiar with this. Machine learning models are everywhere. Every industry vertical, banking, insurance, healthcare, technology, any place you have data, you have machine learning models today. And that's because they're achieving spectacular, the performance is just spectacular compared to state-of-the-art and even human-based science. We're all familiar with all the progress that deep learning has made in classifying images, in translating text from one language to the other, in playing various strategy games, and so on. So it's not surprising that they're spreading everywhere. So that's the good news. Now, the bad news is that these models are black boxes. So what I mean by that is we understand them enough to craft different architectures, different models for various tasks. We know how to train them, how to deploy them. But a trained model is still a black box to us. We don't quite understand how does it internally come up with its predictions. Like, what's the internal logic by using which it makes its decisions? And this causes business risks. So it leads to customer mistrust. If your model is biased, there may be risk of non-compliance. If it's unfair, there's risk to your brand. There's risk to AI management. And this is all over the press lately. I mean, there was the Amazon AI recruiting tool that was found to be biased against women. There is the Uber fiasco, and so on. So for any enterprise that is deploying machine learning models, the following stakeholders are concerned. So there's the business owner who's worried, can I trust my model? The customer support person is worried that if a customer complains, he's unhappy with the model's decision, then how do I sort of answer the customer complaint? Data scientists worry that I've built my first model, but then how do I iterate on it? How do I know where is this model lacking? What are the avenues to improve this model? And then, of course, regulators are worried, are these models fair? Are they complying with local laws, and so on? So what's the technical problem here? So one technical problem is, we asked this question, why did the model make this prediction? In the rest of the talk, we're going to tackle this question. You're given a model, you're given a prediction, and you ask the question, why? Why did it make the prediction? So here's an image of a fireboat. There's an object recognition model that labels this fireboat with 99% probability. So then I ask, why is this a fireboat to the model? Is it the bridge? Is it the water spouts coming from the boat? Is it the water under the bridge? What is it that's causing it to think of it as a fireboat? Here's a more interesting example. This image is labeled as a clog. A clog is actually a shoe of that kind. Why is this a clog? Now, this why question is very open-ended. Right? You're just asking this question, why did it make the prediction? So let's try to pin it down to something more concrete, something that we can solve. So our concrete formulation is the attribution problem. So we'd like to answer this why question by attributing the prediction to features of the input. So given a certain prediction, we want to assign scores to every feature such that the score is proportional to the feature's contribution to the prediction. So for instance, in that clog example, you would then attribute, in an object recognition network, you would attribute it to the individual pixels. Which pixels, how important was each pixel in this particular prediction? In a text model, you would ascribe importance to the words. If you had more structured inputs, such as, let's say, a lending model, which has inputs like income, mortgage, FICO score, and so on, you would ascribe importance scores to those. This is a very reductive formulation of this why question. We are boiling down this big why question to just assigning scores to individual features. But this is surprisingly useful, as I'll try to convince you in this talk. So once you have attributions, what can you do? Well, we can go back to that clog and see why was that image labeled as a clog. So you can debug broken predictions. You can generate an explanation for an end user. So think of a lending model, and now you can explain every prediction and sort of say that your loan was denied because the model said your credit score is 0.3, and here are the reasons why. Once you have attributions, you can try to sort of identify weaknesses in the model's prediction logic and assess how robust is the model. And then lastly, if your model works really well, it's robust, it's fair, it's really performant, then I can use attributions to sort of really get to, okay, how is it reasoning? Maybe I, the human, can benefit, can learn something from it. Imagine a model that you've trained to do drug discovery. As a chemist, I'm interested to know what is the logic that it applies internally. So rest of the talk, I'm going to talk about two attribution methods. One is integrated gradients, which we developed at Google. Another one is a classic method from economics called Shapley values. Then we'll discuss some applications of attributions. And then towards the end, I'll tell you about Fiddler. Okay, so we want to attribute a prediction down to the input features. A naive approach for doing this is you drop the feature, you drop every feature, and notice the change in prediction, and call that the attribution for that feature. So in a text model, you would sort of drop a word, and then notice the delta in the prediction, and call that this particular word in your input is as important as this drop. Now the problem with this is A, computationally expensive because you have to do this for every possible feature. B, it may introduce unrealistic inputs. Now you have these inputs which have certain features dropped, which may not make sense for the model. And 3, this is misleading when features interact. Imagine a prediction where two features have to come into play for the prediction to exist. Now if I drop either one, the prediction goes away. So I'll over-attribute. On the other hand, if it's the disjunction of two features, then I drop either one, the prediction doesn't go away. Okay. So approach 2 is inspired by linear models. So suppose this was a linear model, what would you do? You have this prediction, you want to ascribe importance to every feature. In a linear model, the attributions are the coefficients of each feature times the feature value. Right? That's the coefficient sort of shows the strength of that feature in the prediction. In a non-linear model, this amounts to taking the derivative of the feature, of the prediction, relative to every feature. That's sort of a first-order linear approximation of the model. So we look at dy by dx. So if I apply that to this fireboat image, you get attributions of the image on the right. So the way you produce the image on the right is, you compute attributions for every pixel, and then you scale the brightness of that pixel in proportion to the attribution. So all the pixels that appear bright or white in that image are the ones that receive a lot of attribution. So those are what the model considers, we would say according to this method, those are what the model considers relevant for the fireboat label. But this kind of looks weird, right? Everything under the bridge is being highlighted. Now either the model reasons this way, that whenever it sees bridge and water, then it calls it a fireboat. Or maybe there is some problem with this attribution method. It's not quite reflecting how the model is thinking. Now, when we look at gradients, we are examining the derivative at a single input. So we are perturbing every pixel, roughly, and noticing the change in the prediction. But we are doing this at this single input. Now, if the prediction function is flat, then no matter how much I perturb, there will be no change. So the one trick we use is, instead of looking at gradient at one input, let's look at the gradients at multiple inputs. So let's dial down the brightness of this image all the way to black. And then observe the change in prediction for the fireboat label as I move from black to the image at hand. So when it's black, there's no fireboat. So the network says your fireboat probability is 0. At the image, it's 99% fireboat. Somewhere in the middle, as I'm slowly increasing the brightness on the image, the network thinks that, oh yeah, it's jumping. And its confidence that this is a fireboat is increasing. That's the gradient that's interesting, because there is some activity there. So this plot basically gives us our method. What we do is, instead of looking at the gradient at a single point, let's look at the gradient at a bunch of points and average them. So that's the method called integrated gradients. More mathematically, you take the path integral of the model function along a straight line path. Now with integrated gradients, you get these much better looking attributions. You can see that the water spouts are getting highlighted. These are much more indicative of this image being a fireboat, right? Now that black image, so to compute integrated gradients, I needed this black image, right? This is what I call a baseline. So a baseline is nothing but an information-less input that we are diffing against. So to apply this particular method, so you're trying to explain an input, the method requires you to provide a neutral input. And then it gives you explanations relative to this neutral input. It's saying, relative to this black image, this particular image is called a fireboat because of these reasons. Here are some comparisons between just looking at the gradients and looking at integrated gradients. The first column is the integrated gradient, second column is gradients of the image. Now, I've told you about this method. How do you evaluate it? So how do you know whether an attribution method is good? Whether it's really reflecting the model's reasoning? Well, one idea is whatever features it says are the most attributed features, let's try to drop them. And then notice the change in prediction. The higher the attribution, the higher should be the corresponding change in prediction. But this has the same problems as ablations that we discussed before. I might drop a feature and then I suddenly create this unrealistic input. So I don't know whether the drop in prediction is because I've created a bizarre input or it's because that feature was really important. The other option is to run this by humans. So I produce attributions for images and I ask humans, like I was doing with the fireboat. I was trying to show you the attribution and then convince you that, look, this matches what you and I think of as a fireboat. But this is also a bad eval because it's riddled with confirmation bias. We are likely to accept an attribution that matches our reasoning. But the job of an attribution method is to reflect the model's reasoning. So for integrated gradients, we come up with a different evaluation, which is sort of an axiomatic justification. This is inspired by some methods in economics. So we list certain desirable criteria that an attribution method ought to satisfy. And then we mathematically prove that this is the unique method that satisfies those criteria. Then you can prove a theorem like this. So for integrated gradients, we have a theorem that it's the unique path integral method that satisfies these 6 axioms. So I don't have time to explain all 6, but let me explain one of them. So sensitivity. The sensitivity axiom says that if all else equal, changing a feature changes the output, then that feature should get some attribution. Correspondingly, insensitivity says that if a feature is irrelevant to the prediction, then that feature should get no attribution. Right? So there are 6 such axioms under which you can prove integrated gradients is the unique method. Okay, now let's get to the fun part of the applications. So let's try to debug this clog image. Why is this called a clog? So those are the attributions. If you squint at it, you can kind of see the clog emerging. So it's like an optical illusion to the network. Here's another interesting example. So this is a model that is trained to predict various lung diseases from chest X-rays. The image on the left is the original image, which is labeled as cancer. Now we apply the integrated gradients method to highlight pixels of the image that are most relevant to this prediction. So we attribute the cancer prediction down to pixels of the image. And then we see those pixels highlighted in red. Those come out to be the pixels with the highest integrated gradient. So they seem to be the most relevant to this cancer prediction. So then we go to a radiologist asking, is this some kind of a pathology that the network is focusing on? So the radiologist looks at it and he zooms in and he says, if you notice the place where the red pixels are, you also have a couple of pen marks. So what's happening here is the data on which this model was trained was annotated. Images that had cancer, these are real patient images. Ones that had cancer, the radiologist had marked it. Right? The radiologist had marked the pathology. What the model had learned to do is to detect marking. If there is a marking on the image, it will call it cancer. No marking on the image, it won't call cancer. Now this is something, notice that the marking is a perfectly good predictor of cancer. So your typical accuracy metrics of AUC or held out accuracy wouldn't have caught this. Only when you start looking at the attribution, what is it using to predict cancer, then you realize, oh, it's using this correlated feature which is not causal to the cancer prediction. So in summary, integrated gradients is a very easy to apply method for attributing any differentiable model's prediction to its input features. It's backed by an axiomatic theory, it's widely applicable. There are several applications of it. I've just discussed two, but there are applications to text models, there's applications to models with structured input and so on, to chemistry models as well. But the key thing is, it's only applicable if the model is differentiable. Then you might think of, okay, what about all these non-differentiable models like decision trees, boosted trees, random forests, etc. So here we turn to a classic result from economics called the Shapley value. So this is a golden result in economics. So it's from Lloyd Shapley in 1953. So to explain this result, let me tell you a little bit about cooperative game theory. So the idea in cooperative game theory is that you have a bunch of players, think people, coming together and creating some amount of value, say revenue. Shapley values is a fair way to distribute bonuses. So let's say this group of people came together and created $1,000. How do I then distribute bonuses? So how do I apportion these $1,000 to each one of you such that the attribution is fair? Now, Shapley values is a way to do this. The beauty of Shapley values is that it's axiomatically unique. So under 4 simple axioms, it's the unique method that satisfies those axioms. The algorithm is based on this idea of marginals. So the way to do Shapley value attribution is, you remove a person from the mix and notice the revenue. Then you throw the person in and then notice the increase in revenue. That's how much this person contributes to this set of people. This is called the marginal. Now the marginal will vary depending on what subset of people are present. If this employee is the only employee in the company, then he'll create a lot of value. But then if already there are 20 other employees, then the marginal created by this guy is not so much. Shapley value is a certain weighted aggregation of the marginals. And it's unique under 4 very simple axioms. Now lately, this idea has been applied to explain machine learning models. So the idea is, you think of a model prediction as a game. The players are the features. The features are coming together and creating the revenue, which is the prediction score. And now it's the same bonus distribution problem. You have this prediction score that's been created. What is the importance of every feature in creating this score? There are 2 main challenges in applying the Shapley value method to machine learning models. Applying Shapley values requires you to compute the marginal, right? Which means I take a feature out, then I want the prediction, and then I'll throw it in, and then I look at the change in prediction. Now notice a feature like income. Suppose this is a lending model, you have a feature like income. What does it mean to take the income feature out? Do I make the income 0? But then that's a weird input. You don't have a person with 0 income. So what do? So that's challenge 1. Challenge 2 is Shapley value is computationally expensive, because you need to compute the marginal for all combinations of the other players. Now there are papers to tackle both these challenges. So without going into detail, at Fiddler, we implement both. We have a way to implement Shapley values for non-differentiable models and integrated gradients for all differentiable models. So now what is Fiddler? So Fiddler is an explainable AI engine. Our mission is trust, visibility, and insights for every machine learning model. So our goal is to be able to explain every machine learning model out there. More concretely, Fiddler is a platform where you upload your data, you upload your model, and then you get an insight screen like this one. So here's an example of a credit lending model. So on the top left, you can see the credit approval score given by the model, so 0.3. On the left panel, you have the features. So FICO is 790, salary is 89,000, credit requested is 9,000, and so on. And these features, the prediction is 0.3. On the right-hand side, that tornado chart is the importance of every feature. So in this particular case, the 0.3 prediction is being blamed mostly on the FICO score. On the other hand, gender and marital status are negative factors. So of course, in a lending model, you shouldn't be having gender as a feature, but this is just an example. Now, if you notice the sliders on the left panel, so those are ways to sort of fiddle with the input. So you can perturb the input. So I can change the salary from 89,000 to 120,000. And then this interface will show you the change in prediction, and then you can recompute explanations. So you can see point-wise explanations, and you can also do what-if analysis. What if the salary was this? Now what would the prediction be? A new thing that we are working on is we go from explaining individual points to explaining regions. So let's take everybody from California and take everybody from Nevada. Let's take all the users from California and let's compute the top attributed features for those users. And then let's similarly take the pile of users from Nevada and compute the top attributed features, and then you can compare them. Now Fiddler today does more than just explanations, right? So we also have tools to sort of analyze your data sets. So you can look at feature distributions, feature correlations. You can look at how a certain feature is correlated with the output probability. You can look at partial dependence plots. And then we also have monitoring. So you can hook up your live data to Fiddler and then sort of monitor predictions. So here's an example of monitoring. So you can hook up your live traffic, and then you can see how the features that you're seeing, how your real-time features in a certain time slice are relative to your training distribution. Are the features drifted? During training, you probably saw users which had an income between 100,000 and 200,000, let's say. And now you're suddenly seeing users with 500,000 income. So there's a certain drift that we can show you. Then we can point out the most egregious predictions in a certain time slice. So here are some users that got a really low credit approval score or a really high. And then you can go and explain those points. So you can select one of those points and go back to the explain screen saying, what is going on for these features? Why is this input being given an approval score of 0.99, where bulk of my data is around 0.3, 0.4? So that's my last slide. This is our vision for the future. So we'd like to be a pluggable explainability platform that plugs into all stages of the AI lifecycle. So starting with training, where we'd like to be able to debug and visualize how the model is training. Moving on to QA, where we evaluate and test compliance. Then once you have models deployed, then you can use Fiddler to explain individual predictions. You can use monitoring to sort of monitor how the prediction traffic is. You can do A/B testing to run experiments between different models. And then finally, we'd like all of these insights to go back into the training stage and sort of help you improve the model. So that's the vision, to close the loop. That's it. Thank you for listening. That's my last slide.
How do you measure success of your explainability? How do you measure that you've been successful? Because you can take any feature and say, hey, this is the thing, but is the end user the measure of success, or how do you measure success?
Measure success of explainability? Oh yeah, good question. So actually, that is something that I did not speak to, which I should have. So that top right thing over there, that's audit. So one of the things we enable through explanations is for users to be able to audit the model or audit model predictions. So you're given this prediction, and the explanation is the evidence, and then a human analyst, let's say a credit risk officer, can see, do you agree or disagree with this prediction given this evidence? Then you can sort of note with the explanations, how often did they agree with the prediction, how often they did not agree, and did they find model blind spots through it, right? You could do the same analysis without the explanations and then sort of compare them. That'd be one way to evaluate. Yes?
Very interesting presentation. Does the current platform, Sorry, very interesting presentation. Thank you for all the technical details as well. Does the platform support also at the moment classifier for audio or like videos or raw data like images?
Not right now. Not right now.
Is
But
there
the technology, as I showed you, can
Yeah.
support it, right?
Yeah.
But not right now.
Have you tried anything as research-wise on audio specifically, or just the pictures?
So not on audio, I haven't, but I know that other people have using integrated gradients,
Okay.
but I haven't.
Well, maybe we can have a chat later then.
Sure,
Thank you.
sure, absolutely.
Thank you
yes.
very much.
Yes. Yes.
Actually,
Great presentation.
Thank you.
So me and my team are working a lot on 3 different components to understand AI black box. Influence, explainability, and interpretability. So in explainability, it makes sense. You can use this or you can use attention. Influence in terms of understanding which portion of the training subset was directly responsible for prediction is very crucial because if you have an error, it becomes an auto-correction mechanism.
That's right.
So can you talk about that a little bit? But it seems like a very challenging problem to solve.
Right. So if I view this through the lens of attribution, then what you're saying is you want to attribute a prediction down to the training examples. So in a sense, you're attributing through the training process all the way down to what examples went in, right? There's the famous ICML 2017 paper to do that. Now, we are also working on an attribution-guided influence. So the intuition, this is still research that we're working on. The intuition is attribution sort of reflect how a model is thinking. So now 2 examples that are similar in the model's eye will likely have similar attributions. So one way to get the influential examples is to cluster in the attribution space. So you take these attribution vectors, like what the tornado chart is giving, and then you cluster in this space. So a training example that has a similar attribution distribution would likely be influential to this particular prediction. So that's one angle that we're exploring. The ICML 2017 work is very expensive to implement. So that's right. So for that reason, but if you know of a fast implementation of it, we would support it.
That's a brilliant exposition. Thank you. Just coming back to that point where in the explainability scenario, right? When a human operator detects something that they would disagree.
Yes.
Right? So does the tool provide the insight into what is the inflection point at which it decided that it kind of chose to go the other way?
Do you mean the model chose to go the other way?
Yeah.
So when it flipped?
Yeah, when it flipped. What was the decision where it caused it to flip? So is there a way for you to kind of go back and debug and kind of get some insight into it?
So such an analysis you can do through this what if sliders over here. So you could, for instance, so now in this particular example, I bet you that if you take the salary all the way to the left, so if you reduce it, then the score would go up. This is credit approval. So if you take it to the right, then the score will go up. And so you can sort of see when it shifts from a certain threshold. This is right now threshold agnostic because we are explaining the raw score.
Gotcha.
But you could slide and see, if you have a threshold, then you can see when it goes over the threshold. Does that answer your question?
Yeah, sort of we kind of play around with it to see
Yes.
what point it
Yes. Yes.
Got it, thank you.
Have you applied Fiddler to understanding more about your training sets?
So not these explanations. So the thing is, these are point-wise explanations, so you can try to explain the prediction on a training example, but you're saying more holistic at the level of the data set.
Yeah, like the Claude example. So maybe you didn't have any sample chosen in the set at all, and there were no labels, so that was the only choice.
That's true. That's true. So we've done that kind of analysis, but manually. So, that's exactly how the tool helps you. So the tool points out that, well, it's thinking of that particular boy as a clog. Then that gives you the insight, why is this a clog? Because it's red. and maybe the training examples that I have are all red clogs. Maybe I should go and get a blue clog and throw it in my training mix. But this is exactly where the human has to come into play. The human analyst has to take that step, augment the training data.
But even just a pointer to where in the training set that there's a problem is useful.
Sure, yes. Thank you so much.